A dynamically consistent synthetic event set of windstorm footprints over Bangladesh with characteristics comparable to high-resolution numerical weather predictions has been developed in collaboration with Oasis and Bernd at the Met Office. The purpose is to improve the assessment of the hazard component in risk modeling. Two sets of weather and climate data with distinct scale representation are combined in a statistical downscaling process. Data from coarse climate model simulations and high-resolution reanalysis data are merged after careful scale selection using pattern similarity and contour mapping in a statistical model. More than 6,000 storm footprints are available for further assessment of windstorm risk over Bangladesh. This report describes the methodology. What is an event set? Event set is a large set of insurance-relevant events. The aim is to describing the upper tail of a hazard distribution. The purpose of that is to do disaster cost mitigation planning, insurance pricing. The issues here is often that no point-wise observed climatology, hardly any good quality observations are available, and only large-scale assessment of extremes from reanalysis or from climate simulations is available. That leaves us with a scale gap in the requirement. Large grid box wide assessment of extremes with respect to point asset exposure. In this exercise, we aim to overcome the scale gap. We're using climate information from the Primavera experiments. We're using Primavera unseen climate cyclones, where we use the Primavera experiments, the Primavera cyclone tracks, and that's what we use for event selection. On the right in the animation you see aspects, you see the final event set of the 6,000 storms, just for you to give you some eye candy and to keep you interested in this presentation. We are applying a downscaling method that is concerning scale separation, pattern matching, and event set creation. In the end, I will speak about some caveats and give some future ideas. So, from the Primavera runs, which is a large set of state-of-the-art climate models, which are candidates for the CMIP6 climate model intercomparison project coming up. It's a coordinated set of experiments that has been designed to assess both a standard and an enhanced horizontal resolution simulation in the atmosphere and the ocean. We pick available simulations for the period 1950 to 2014 at 25 kilometer resolution. There's a 3-member ensemble, coupled ocean model runs with contemporary forcing. There's a 3-member ensemble with atmosphere-only runs. There's a single coupled run with a high-resolution, 8-kilometer high-resolution ocean, and a single coupled run with fixed forcing for the 1950s. These 8 contemporary realizations of current climatology give us 520 years. More information about this experiment may be found in the shown links. We select storms in the following way. We utilize the Hodges maximum gust along a track. Hodges has defined a storm tracking algorithm that is giving several pieces of information, where of interest to us here is the maximum wind speed along the track at 925 hectopascal height. Here are some location maps of this particular point of the maximum wind speed from several of the Primavera runs, and we have chosen a criterion of this wind speed, a long track wind speed, to be higher than 20 meters per second, and in the box covering the Bay of Bengal and Bangladesh. From the runs of the 520 years in total, we have selected 557 unseen, large-scale, climatologically sound, meteorological consistent extreme events, cyclones over Bangladesh. So the selected unseen coarse resolution cyclones are animated here in the center of the picture. This is showing the maximum gust over a 3-day period. These are dynamically consistent. They give us the broad features, the large scales, but They show only weak extremes. They are not observed. They have no observed equivalent. They're unseen storms. So what can we do now to sharpen the features and bring out the extremes as if they were observed? Remember that the dynamical downscaling, dynamical modeling is prohibitively expensive. So for the IKI event set, we have two basic data sources and two new ingredients. The data sources are the Primavera current climate simulations at 25 kilometer resolution, which is where we have 557 unseen tropical cyclones, and the ERA 5 historical cyclone catalogue at 4.4 kilometer resolution. From that exercise, we have 110 individual events. The aim in the exercise is to build a large set of realistic storm footprints. The procedural ingredients are scale separation and pattern matching. The Primavera events provide dynamically consistent and plausible storm events resolving the large scales. The historical catalogue provides detail missing in the Primavera set of the wind gusts up to 4.4 kilometer resolution. This helps also correcting the unresolved orographic detail. And this is a sketch of the DOWNscaler. The new ingredients are scale separation and the heraldic measures for pattern matching. And the story goes as this. In the top left blue box, we take the historical, about 100 storm footprints, and we separate the scales into a high resolution and into a low resolution component. On the right hand side, we have the low resolution climate runs from the Primavera experiments. We have selected circa 600. So now we apply a pattern matching step where we take for each Primavera run a number of best matching high resolution, low resolution historical storm footprints. We keep about 10 or so and proceed to the next step. That gives us 6,000 storms in total. The next step is to quantile matching. That is done between each pair of the historical and the Primavera low resolution storm footprints. And finally, we add the small scale features that we have separated out initially from the high resolution runs onto the pattern matched and quantile mapped storm footprint in detail. So the scale separation works like this. It is inspired by a lecture that I've seen on computer vision. On the right-hand top right-hand side, you see an image, whereby this method is just for fun, matching tiger stripes with leopard dots. Each of the images is Fourier analyzed, and we can do the same for the storm footprint, and that provides us a distinct resolution-dependent histogram of the magnitude spectrum. The coarser the resolution, the tighter the histogram. We can separate the scales in the high resolution 4.4 kilometer storm footprints by low-pass filtering, and by subtracting the low-pass filtered part from the original to retrieve the high-resolution part. We can tune the separation point by averaging the storm footprint so that it matches the histogram of the resolved scales of the 25 kilometer Primavera step. So that means that we have then a means to separate the scales in the high-resolution storm footprints at exactly the same equivalent resolution in the low-resolution unseen Primavera footprints. Now we have scale separation to make the low-resolution part of the historical catalogue comparable with the Primavera unseen current climate simulations. This yields the high-resolution random, but physically plausible view of unresolved gust details at 4.1 kilometers, to be added later. So the image in the middle shows a little bit about what is meant. The top image shows the complete high-resolution footprint. The low-resolution part is shown in the middle, and the high-resolution part is shown below. And here you see the low and the high-resolution components of the historical footprint, of the historical catalogue. Left, you see the low-resolution part, which is averaged down, and on the right-hand side, you see the residual high-resolution part. And these are the components that we are recombining in the dynamically consistent statistical downscaler. So, how does the pattern matching work? The pattern matching needs sufficient discrimination that, even between very similar images or storm footprints, this discrimination remains measurable. And the measure that we're using is the heraldic texture features. On the top right-hand side, you see an image of Mr. Heraldic, which I'm extremely grateful for, because he defined the method of deriving from the gray level co-occurrence matrix defined over an image to be the distribution of co-occurring values at a given offset, which contains information about how images in pixels with a certain position in relation to each other occur together. There's a Python package called Hodges, which is giving us the tools to do this calculation of the 13 features for each of the storm footprint. The detail of the features of the individual statistics is not relevant. Important is that in the combination and in the way that they are derived for each image, they bring down the image dimensionality to a very low number. It's compressing about 1.5 million bit points to about 56 numbers, but still retaining the discrimination that we need to proceed with the next step, which is evaluation of proximity, evaluation of close matches. In each similarity measure of the storm footprints, we note the distance and rank for each of the measures. We also calculate the cosine similarity between measures, vector. We calculate a full field differences which are expensive. That's the Frobenius norm and the dot product. And we evaluate the 4 similarity measures by rank sum and pick the top n best matches. Evaluating the similarity between images is not trivial. That's why we use the 4 measures. That yields the pattern matching, enables us to select the most similar, say 5 to 20 storms from the historical catalogue for each of the unseen core storms, providing a physical plausible view of unresolved gust detail at 4.4 kilometers. And this is an example. On the top left, you see one of the coarse storm footprints from the Primavera runs. And shown with it are 11 best matches of the low resolution components of 11 historical runs. And you see that the matches are reasonable and we can work with that. But that's a demonstration of how the pattern matching works. Putting it together, I bring you an example here of a previous project that we did for European windstorms. So here on the top left, you see one full high-resolution complete storm footprint. Next to it in the middle, you see a low-resolution storm, which is fairly similar, but you see much broader features, much lower extremes, and so forth. On the right-hand side, you see the low-resolution component of the full picture on the left, which is showing a much lower resolution image. On the bottom left, you see the high-resolution components that have been subtracted from the complete storm footprint. Below, to the right, in the middle, below, you see the LRQQ, which is the quanta-matched low-resolution storm footprint, and you see that already the value range is equivalent to the value range of the high-resolution, low-resolution part. And on the bottom right, you finally see the quanta-matched combined image, and the similarity between the top left and the bottom right is striking, and the features are about similar, and it would be difficult to distinguish and to say clearly which one of the two is a complete NWP forecast output and which one is a synthetic storm footprint. So that is the recombination part. And here I show 12 storm footprints for Bangladesh. You see they're all showing high features, high resolution features. They all show a reasonable range of extremes, and they are by eye indistinguishable from the high resolution historical cases. So in summary, the dynamically consistent statistical downscaling works by scale separation to match similar storm footprints between the unseen storms and the historical catalogue, but also to add the unresolved high resolution scales onto the unseen dynamically consistent, plausible, but low resolution storm footprints. Pattern matching is a method to find similar storms so that we can argue the high-resolution scale from the historical catalogue is a plausible match to bring physical detail to the unseen storm footprint. Oh, bloody hell. recording overloaded. Consider turning down video settings or using something else. I will continue as we are. The take-home messages are framing a research interest into an event, defining the geographic and the time boundaries really helps comparing different realizations of events. CDFs are really useful when comparing large number sets, model fields, or time series with a view to risk. The scale separation allows scale-dependent attribution of cause and effect. And in this methodology, there's a lot more potential for machine learning applications. But there are caveats, and on to the caveats we come next. The Primavera cyclones are bigger and less intensive than the Era 5 cyclones. The Era 5 cyclones span only 11 storms. With goodwill and assuming the 9-member ensemble spreads between independent members, the set may be interpreted as 99 events. This does not describe the expected full range of cyclones over Bangladesh. Currently, for each Primavera event, circa 5 to 20 Era events are selected. The best matching pairs between Era 5 and Primavera may still have a sizable distance in event space, i.e. are dissimilar with respect to location and in particular orientation. Reducing the best matches to perhaps 7 or 8 might help homing in on better matches, given we cannot create more high-resolution events, because that is too expensive. The 11 Era 5 cases show bimodality. The storms Rajmi, Sidra, and Viaru are relatively weak. Ayala, Ruano, and TCO1b are strong. Akash, Bob 1 and 2, and Mora hang somewhere towards the middle, leaving a gap in the distribution. The modeling outlook I want to describe like this. Consider you're able to build a machine that is learning the high-resolution features for the low-resolution unseen storm footprints from matching the stack of 100 historical high-resolution events. This would then allow to draw new high-resolution maps for each low-resolution footprint, sharing the features of near neighbors. But that is future work. We may engage with that next year. Assume that the scale relationship between small-scale and large-scale weather phenomena remains the same between this beginning of the century, maybe the end of the century. In that case, we could replace the Primavera low-resolution current climate cyclone events with Primavera future cyclone events and compare, if we accept the current downscaling model. I highly recommend to read the scientific documentation for the Bangladesh Tropical Cyclone event set, which is available on the Oasis platform. Thank you very much.